apologize for that. A lot of today is basically, and that's not the page I want, a lot of today, go away. Got a window that's in the wrong place. Right. So here we are. These notes are already in Canvas, so you don't need to write anything down unless you feel it's absolutely necessary. We're going to talk about all sorts of things that happen in observational and when you're looking at controlled experiments, right? So controlled experiment, right? You have two groups. One's called the control group. The other is called the treatment group. You make sure that when you pick the people to go into each group that you do it in a very random way, right? You don't say all the tall people go into the first group and all the small people go into the second. They're random. If you want to do a good experiment, I think it's pretty obvious that you should have a large enough sample, right? Don't do a sample of 5 people, right, in each group. That's a totally 10, and say, I've now got evidence to prove that this new drug is better than the old drug. Would you agree? 5 people could just be a fluke, right? You need hundreds, if not thousands, to do a good group. There is also in controlled experiments a problem with what's called adherers and not adherers. People volunteer to take part in experiments, right? And sometimes it's a clinical trial and, you know, they're taking part in it because there's a new treatment. They don't know that they're getting the new treatment, but they could be, right? They might be getting the old treatment, but they do it because very often the treatment's free, regardless of which treatment you get, right? So if there's a new treatment for reducing the effects of multiple sclerosis, a lot of people will volunteer for that because they think, well, you know, this could be the new wonder drug and I could be one of the first people to get it. And so they do that. But unfortunately, some people drop out of the experiment. And sometimes for good reasons. You can imagine that there's 2 drugs being used to cure or to reduce headaches. And you happen to be in a group that's getting the new drug. And instead of making your headaches less often or less severe, it's actually not a good drug. It gives you headaches, right? It gives you more headaches, and the ones you get are worse. Can you imagine that you're going to say, I'm going to stop taking these pills. These are making me worse, not better, right? You are basically a non-adherer then, right? You have dropped out before of the end of the experiment. Now, if you're collecting data, it's not a good idea if only some of your people are there at the end. And you could then say, well, for the people we had at the end, we got really good results. But couldn't that because 80% of them dropped out because the stuff you were giving them was bad, and only the 20 that were left did it work with? Now, I don't want to take a medicine that's 20% effective and 80% worse than having nothing, right? And so your data gets corrupted badly because of that. Now, observational studies, and one of the biggest problems they have is a guy called lurking or confounding variable, just another name for it. Now, a lurking variable creates an association between the two that tempts you to think that it's the cause. So the story I could have here is, imagine the TV story, right, against life expectancy, right? The number of TVs that a country has per household, the average number of TVs against how long people live. Remember that data was quite high. And then we said, hey, owning TVs makes you live longer, right? That would be an example of a lurking variable, because TVs wasn't really the reason. Wasn't it wealth of a country that meant you could afford TVs, lots of them, that was being reflected? So a confounding variable is a dangerous variable, you know, to cause problems with. And here's another story you can read. Now, observationals tend to have 2 versions. One is called a retrospective study, and the second observational ones are called prospective study. Right, let's talk about a retrospective one first. This tends to be very often quite common. Imagine you've got a situation where there's a very rare form of cancer, right? I'll call it the Robertson cancer, right? It's very rare, like 1 in a million people ever get it, right? Most doctors never have a patient in their entire life that ever had Robertson's cancer, right? It's that rare. And then doctors start noticing that they got 1 or 2 patients with Robertson's cancer. And they talk to other doctors and they say, yeah, I thought I'd never see one. And I got one 5 years ago. And then they talk to other doctors, right? They're at conventions and they have conversations about, weird things or unusual things. And they start noticing that there's a lot more Robertson cancers than there typically used to be in the past, right? So what they would do there is they do a retrospective study. They would go back and collect data for the last 50 or 100 years, whatever they could get. And they'd look at how many people, as a percentage of, everybody, actually had it. And let's suppose for a long time, it was like 0.01% ever got it. And then it went up to 0.1%. And then 5 years later, it went up to 0.2%. Red flags would be going, right? The CDC would be saying, what the heck's going on here? Why are we catching this? Why are we getting so much of this cancer? A lot of cancers can be triggered by things, right? Carcinogenics, right? Smoking causes lung cancer, right? That kind of thing, right? But other cancers get caused by, isn't there a talcum powder one that's being sued because it's causing ovarian cancer, right? And, could be eyeshadow, right? Who knows what it is, right? Chemical looks benign, but actually it causes problems. So they're looking at all the people that had Robertson's cancer in the last 50 years, and they try and find something in common, right? Do they all drink the same kind of beer? They all work in the same kind of job, right? Are they all farmers, right? Because DDT, right? Remember that one? It was causing a lot of cancers. The people who were using, I can't remember what the weed killer was, but there was a weed killer that's actually causing cancer, right? And so they go and look at it and they find out that it's only people, most of them anyway, it's only people who work in slaughterhouses that are getting it. And they think, what on earth are you doing in slaughterhouses? And then they go and look at it, and maybe there's a chemical that you use, to clean up the floors. And now they've got a good candidate for what's causing Robertson's cancer, right? There's a chemical that they use to clean up the floors, and that chemical's got a carcinogenic, and that particular carcinogenic causes Robertson's cancer. And then the company that makes that bleach, whatever it is, gets sued by everybody who's got Robertson cancer and proved that they, were around it a lot. So that's a retrospective, right? You go back and see if you can figure out what's going on. They had an example of that. Anybody heard of Legionnaire's disease? Never heard of that? Right. Legionnaire's disease is basically, it's a lung disease, right? It's airborne, it affects your lungs, very serious. People die of it, right? It'll kill you. And it's called Legionnaire's disease because it was never heard of. Nobody had these symptoms before. And there was a veterans, Legionnaires, right? Veterans conference going on. And a lot of the people at that conference, weird term, but a vague term, were getting it. And they couldn't figure out what it was, right? And, they went back home and they caught, the symptoms, 2 weeks later, they got the symptoms. And they were trying to figure out where all these deaths were coming. Why were people just reasonably old, but quite healthy, dropping dead with the same symptoms, all based on lungs? And they tried to figure out what the connection was, and they found out that most of them were, at that conference. And then they found out that in that conference, they then narrowed it down to one building. And then they narrowed it down to, on the top of that building, there was an air conditioning system that used basically water. And inside that water, the new Legionnaire's disease virus was living. And what it was doing is that when the water gets sprayed into the atmosphere, people were breathing in this water with the Legionnaire virus and getting the Legionnaire. And luckily enough, they caught it early enough, disinfected the thing, took care of it, and that was gone. If Legionnaire's disease had been person to person, if it you could have caught it from someone that had it, that would have been like the new COVID. That would have ran rampant because, you cough, you sneeze, somebody else catches it, they cough and sneeze, the way viruses work. But this one only could be caught directly at the source, right? From that sprayed water that had the virus in it. So it's very pernickety. And that's an example of it. There are tons of these and they're really good. Well, for me, they're really interesting. How you get those. And I've got stories there about that type of thing. Right, now, there are tons of different ways of sampling, right? Collecting a sample. Here is a list. It's not inclusive, but it's a good example. There's simple random sample. That is actually the gold standard. In a simple random sample, every single member of the population has the same chance of being picked for that sample as everyone else. Right. So when you do a simple random sample, anybody in the population could get picked. And that means your sample is a very good representation of the population, right? And there's some details on what that looks like. Let's look at a systematic sample. Right. Suppose I was interested in finding out, what's this one? I wanted to know the average height of OC students. Right. Now, in a simple random sample, I would randomly pick 200 OC students, right, using some random method so everybody had the same chance of being picked. But in this systematic sample, we take everybody in OC as a big list and we pick whoever was number one, right? So Aaron Aardvark would get picked. Then 100 people later, 101th person, then the 201th, then the 301th, and all the way through. So we would pick the people for a sample using some kind of systematic method, right? Suppose I wanted to know the heights of OC students. Couldn't I just pick somebody whose last name started with an A, somebody whose last name started with a B, C, D, all the way through to somebody whose last name was a Z, right? That I could do my sample that way. That would be an example of a systematic sample, right? Now, you might think, well, that seems pretty reasonable, and a lot of times it isn't. It's not a good idea to do that in Scotland. If you picked one person or 10 people whose last name starts with an A, B, C, you wouldn't get a fair distribution of what Scottish people are like. And the reason for that is there's an awful lot, more than 50% of Scottish people's names start with an M. They're McPherson, they're Mac Gregor. Can you see the problem? Aren't you only going to pick a small portion of Scottish people who have an M in it? And who starts with Z? Well, virtually nobody in Scotland has a last name of Z. So that probably means that that person was an immigrant from some other country. So you're not really getting a good picture of the entire population of Scotland, aren't you? Kind of cherry picking unusual names and giving them more preference and missing out a huge chunk of typical Scottish names, which starts with M's. I'm an exception to that. Robertson doesn't start with an M, but that's okay. I finish with a son, which is mostly what happens if you don't start with an M, you finish with a son. Right, the next one is a stratified sample. Now, this is when you break a population down into particular categories or subgroups, and then we choose people at random from these groups in the same proportion that they exist in the general population. Right. Let's suppose I'm interested in who's going to vote for the next election. And I know that 52% of Bremerton is female and 48% is male. Then I would have two stratifies there, right? It's two strata, males and females. So I would make sure that I picked 52% of my sample would have to be females and 48% of my sample would be random males. That would be an example of that. Right. Now, if you want to make a big version of that, suppose I wanted to know how you're going to vote in the presidential election, right? There are 50 states in America, agreed? Now, you could say, why don't you just pick 10 people from Alaska, right, and 10 people from Mississippi? Why you just don't choose at random 10 people from all those states, right, and that would get you 500 people? Well, the reason why you don't do that is, aren't there an awful lot more Californians than there are Alaskans? So shouldn't you, if 20% of America is Californian, shouldn't you pick 20% of your sample from California, right? Does that seem a fairer representation, right? And that's what you do. And you might say, well, does it matter? Yes, it does. I'm pretty safe in saying this. Would you agree California is very democratic? Right. I don't know what Alaska is, but can we pretend it's very republic anyway? Can you see that picking 10 of each isn't fair? So that would be why you would choose and how you would choose it. Now, a cluster sample sounds the same, but it isn't quite. Okay, in a cluster sample, what you do is you find a cluster, hence its name, that's important to you. So, two stories to give you an example. First one, suppose you are interested in how many high school students come from single parent families. Right? Now, if you wanted to know that as a national thing, it'd be very expensive, right? To do a random sample, right? You'd have to take every high school student, and there's millions of them, right? Randomly pick 1,000, go and find them and ask them, right? Cheaper way of doing that. Randomly pick 10 high schools in America, right? And in each of those 10 high schools, ask every single student, find out at least if they're from a single parent family. So the cluster there was high schools, and there's 10 clusters, right? And you ask everybody. Another story. Suppose I'm interested in nurses' opinions, right? Nurses who work in hospitals, opinion about abortion. If I did a cluster sample, it's relatively easy to do, which is why we do it. Couldn't I find 20 hospitals in America? I'm sure there's a register somewhere that tells you all the hospitals in America. Couldn't I randomly just pick 10 hospitals? And then for every one of those hospitals, don't I just ask all the nurses there, are you in favor or against abortion? That I could do with a relative little money, and it'd be pretty easy to organize. If you wanted to do a simple random sample, wouldn't you have to have a list of every single nurse who works in a hospital in America? I don't know if that list even exists, but if it did exist, wouldn't you then randomly pick 1,000 nurses? Then you'd have to find out where they live. And for every single one of them, you'd have to contact them. Can you imagine how much work that would be and how much money it would be cost to do it that way? So in a cluster sample, it's much cheaper. Most of these other methods are because they're cheaper, right? You get good data sometimes. If you do it right, you get good data, but they're easier to do, they're cheaper to do. And then we have a convenience sample that no one should ever do, but guess what? They do it a lot. A convenience sample is a name given to any kind of sample which you basically don't make any attempt to be fair. Couldn't I just go to a mall with my little clipboard and ask the first 200 people that pass me by whatever it is I'm interested in, right? You know, what's your height? who you're going to vote for, right? Whatever the question is. That's an example of convenience sample. Would you agree people who are in malls aren't necessarily a fair representation of anything except people who go to malls, right? Not a good sample. Dead easy to do. You agree? Just go out in the street and, you know, first 100 people that go by you, ask them whatever it is you're asking. You should never do it, but they do it. You ever heard of random digit dialing? Have any of you been a victim of random digit dialing? They have computers that randomly ring telephone numbers. Not all of them exist, but if you do enough of them by computer, don't you get through to some numbers? Have you ever had a ring on your phone and there's nothing at the other end? You've just been randomly digit dialed. What the computer then does is it says, oh, that number exists, right? There's a person at the end of that. And they store those phone numbers, and then they sell them to companies. And what companies then do is they phone you up and say, hi, we're interested in doing a survey about blah, 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 and they get you. Or they use their own computer random, digit dialer. And when it gets through to a person, they ask you the question. That has a lot of problems. A lot of these things get blocked now. Do you have this thing that says, on my phone, it says something like possible scam? You ever get those? Random digit dialing very often shows up as possible scam. So those people, unless I accidentally don't look and I answer the phone and then I find that nobody's there, those are pretty bad now, but they are very cheap. Here's one called internet panel sampling. Here's one called multi-stage sampling. Right, multi-stage is basically when you combine a couple of methods together, where you do a kind of cluster sample with a convenience sample, right? Something like that. Plenty of permutations. Right. So let's look at what could go wrong in a sample. Pretty much covered these, so I'll do them quickly. You know, asking 4 people is not the same as asking 4,000. Would you agree sample sizes should be big? Don't make any conclusions if the sample's small. We even have tests that tell you how big a sample should be before it's okay to use. I won't tell you that now, you'll find that out later. You know, the way you ask a question can certainly be important. You should ask people things like, which political party would you vote for in the next election? I think that would be a pretty unbiased question. But if you said, will you vote for a pro-tax, big spending Democrat party, right? You're probably biased. Can you remember the one about would you kill an unborn child when you're asking about abortion, right? That is not a good way to ask the question. Honesty in answers, right? People tell lies, right? Or don't for all sorts of reasons. Under coverage. This is when you pick a sample and for whatever reason, there's a large group of people who are missed from your sample, right? That never get asked, right? And if you do that, you can certainly cause problems. So back to politics. Suppose I'm interested in, who's going to win the next presidential election. And the way my sample worked is that I didn't ask people who were working, right? So the way I collected my data, people that were working, there weren't a lot of them in my sample, right? Can you imagine that if there's not a large, reasonable proportion of working people, wouldn't your data be distorted? Because wouldn't that group of people might vote one way more than another, right? Suppose my data had more men in it than women, right? 60% were men and 40% were women. That would be a bad idea for politics, because don't women and men tend to vote differently? right? Not, not all women vote one way or whatever, but there is a difference. And of course, people who don't talk to you are a bad sign, because those also screw up your data.
Could I though?
Mm-hmm.
I know that in some cases, a number of people who aren't answering can be useful, since it can be a gauge of how, in cases where there's an exceptionally high amount of people not answering, it can be a sign that that question is sensitive, or they have views which they worry might be sensitive, like asking someone in a war-torn country if they support like one
Russia.
side or the other.
Yeah. Yes. I mean, once you know that there's a lot of well, that one would be more non-responders or lies. I would think of that particular scenario. But the one I'm talking about is that you didn't even ask them that question, because they were never in your pool to be asked.
Sorry,
That's a little bit different. But you're right, that causes problems. If you ask people sensitive questions, they very often don't want to answer, right? That's a non-responder when that happens. Right, so where are we? We are sampling methods. Yeah, and I'm going to zoom over. Here we go. And I've got the key. Is that sampling methods? I don't think I want sampling methods, do I? Oh, yes, I do. Okay. I'm going to talk now about conservative margin of error. And I think they call it what do they call it now? 95, approximate, there's the word I'm looking for. And the second thing is called the approximate 95% confidence interval. So let's assume that we collected good data, right? We're comfortable that the data we've got is a fair representation of the population. And now we want to work on, is there any way to condense the information into something meaningful? So if your sample size is, say, 200, the conservative margin of error is 1 over the square root of n. Remember that guy? 1 over the square root of n. So we will go 1 divided by the square root of 200. In this case, as a decimal, to 3 decimal places at least, it's that. If you do an answer using decimals, the key word to look out for here is proportion. So if they say, give the answer as a proportion, they want that. You also very often want to convert it into a percentage. I like percentages better, so for me, percentages more sense. So let's suppose then that you collected 200 people and your sample p hat was that 0.31 or 31%, like Pepsi, more than anything else, right? So the conservative margin of error is 0.071 if you want a proportion. If they say, what's the conservative margin of error? And they say percentage, you use this one. Now you want to do this second piece, a 95% confidence interval. It's whatever your sample happened to be, in this case 31%, give or take the conservative margin of error. Now if you want to work with proportion, then you need to make sure that proportions go with proportions. If you want to do percentages, you make sure percentages go with percentages. So let's do both. If it was a proportion, it would be 0.31 plus or minus 0.071. And that would come out, because I'm not going to do that in my head, as 0.31 take away 0.071. And I get the answer nothing 0.239. And if I add it, I get 0.381. And that interval is what we call a 95% confidence interval. We are essentially 95% sure that the real answer for everybody in America that like Pepsi better than anything else is somewhere between what, 0.239 and 0.381. Now, if I do that as a percentage, which is why I like percentages better, it's 31 plus or minus 7.1%. And that ends up being 23.9% all the way up to 38.1%. So we could be 95% sure that the percentage of every American, right, all 330 million of you that like Pepsi is somewhere between, what, 23 and a bit, let's say 24 and 38%. And we did that from a sample of 200 people, but a good random sample of 300 people, on which 31% of them said, I like Pepsi. That's pretty powerful, that you can find out the opinion of every American with a certain degree of accuracy. Now, do you notice it says 95% confidence interval? That's the optimist in me. If I was a pessimist, isn't that also, there's a 5% chance that I screwed up and the answer's nowhere near these numbers. 95% sure is also 5% unsure. Right, so there's two sides of the coin. So you can do this, and 95% of the time, the interval you get will be right. Right, the real number ends up being in that interval. Right, 95% of the time, but 5% of the time, won't you be wrong? Right, just the vagaries of randomness. Can't you just get a lot of people that don't like Pepsi? Right, it just happened to be that 200 people, all sorts of things can happen.
And P with the pi means population portion?
Yes.
Prediction?
P hat is sample proportion, which is basically what your sample said. So in your sample did, 31% of people in my sample like Pepsi, right? That's what P hat is, right? The people in it. Okay, so I am going to do one of these types of questions with you lot. So we're going to collect some data. There's 2, 4, 5, 10, 15. There are 17 of us. So let me start by saying 17 is a horrible sample size, right? It's far too small. But I'm going to do a little cheat after we do the real data. Down at the bottom, do you know the little guy that has reactions and you can say thumbs up? See that guy there? I've got my thumbs up. So I'm going to do a very simple yes/no question. So you only stick your thumbs up if it's a yes, okay? So here goes. How many of you have been to another country in the world? 1, 2, 3, 4, 5, 6, 7, and I'm 8. So P hat is 8 out of 17. So let's show you how we would analyze our sample. "17 people, at least I think I counted 8 out of 17. Now, 8 out of 17 is not very helpful. It's a weird fraction. So I'm going to turn it into 0.47 to 2 decimal places, which is now going to become 47%, because I like the 47% answer. Now, the conservative margin of error is 1 over the square root of n. It's 1 over the square root of 17. And on my calculator, 1 divided by the square root of 17 ends up being 0.24, which is 24%. So my estimated 95% confidence interval is the sample plus or minus the conservative margin of error. So since I'm doing the percentage version, 47%, give or take 24%. So that's, take that away, that's 23%. And if you add it, it's 71%. So with a big caveat here, if you lot are a fair representation of all Americans, which I don't think you are, but if you were, based on the data that we've got, somewhere between 23% and 71% of Americans have been to at least one foreign country. You see how we can use that to predict a bigger picture, right? Okay. Now, I'm going to cheat and imagine that it wasn't 17 people, but I had actually asked 17,000, right? And we're going to keep the answer the same, just for consistency. 47% of this sample said they'd been to a foreign country as well, right? Before I do the calculation, do you think the conservative margin of error is going to be 24%, the same, more than that, or less than that? What would you expect?
Same.
You'd expect the same. Any think it's going to be more? Any think it's going to be less?
I think it'll be less.
Oh, let's find out. If we do 1 divided by the square root of 17, 1,000, the answer ends up being, if I round it off, 0.01, which is 1%. That is a significant difference, isn't it? Now you might think, why on earth is it so small? Well, if you ask a lot of people, won't there be less error? Your answer is going to be more accurate. And the formula reflects that. Isn't 1 over a big number smaller than 1 over a small number, right? Isn't 1 over this guy, right, a smaller number than 1 over that? And there is your first truism, which is true for every sample. Isn't big is better. Bigger samples, better data, right? Better conclusions. Now, in our story, it now becomes 47%, give or take 1%, which is what? 46% to 48%. Isn't that a very narrow window that we're now 95% sure is true about Americans, right? Somewhere between 46 and 48%. That's a really narrow window. Now, if you asked 1 million people, and only Bill Gates and people like that could even afford that kind of money, right? Can you imagine how much money it costs to ask 1 million people in, right? All the workers you'd have just to do that. If you could do that, this would reduce to almost on top of the answer. Could you imagine that in that case, you might not be exactly correct, but wouldn't you be like 4 decimal places good, right? You'd almost nail it on the head. So bigger samples are best. As long as you pick a good random sample, that is true. Luba, have you got your hand up for a question, or you just haven't put your thingy down? Okay. So let's assume that I did a sample on an election day, right? And the sample I did is very often called an exit poll. right? So that's people who went in, voted for whoever they're voting, and you catch them on the way out. Now, those type of samples tend to be the best for accuracy. And the reason for that is those people have really voted. Do you know if you ask someone in the street who you're going to vote for, they might say, I'm going to vote Democrat, they might say, I'm going to vote Republican, but isn't there a good chance that quite a few of them don't bother voting at all? And you see in that case, it's your predictions is going to be a little bit out, right? Especially if more of one party decide not to vote than the other, right? So imagine that I did this, I did an exit poll, and the answer that I finally got, was 49% to 52%, right? That was my 95% confidence interval. And if you were watching the TV program and this was Kansas, and they said, okay, the exit poll for Kansas is that the the Royalist Party has got a vote somewhere in there. Now, what they would normally do in this case is they would call it 50.5% plus or minus a margin of error of 1.5%. You ever seen that? That's what it would look like. They very often tell you that number and mention the margin of error, right? So the Royalist Party has got 50.5% of the vote. That's what we think is going on. And the margin of error is 1.5%. So if you're wondering where that guy comes from, you can see it comes from down here. Now back to the question I'm trying to get to. You didn't know this, but I went to Kansas and became a Royalist candidate, so I could get voted into the Senate. Didn't know that because it's not true, but for my story it is. Based on this data, should the TV station say Robertson has won Kansas, Kansas has gone Royalist, whatever you phrase it as? Should you be able to fairly say that based on what I've told you? So I see some nods. So let me try and dissuade the nods and say why you shouldn't, even although sometimes they do. People will say, well, he got more than 50%, so that means you win. Well, yeah, but that's only the sample. When you convert it into this interval here, we are only 95% sure, right, that they got between 49 and 52. That means, couldn't I get 49% of the vote? Couldn't that be what I'm going to end up with, right? And if I got 49% of the vote, we'll assume it's a two-horse race. Wouldn't the other guy have got the other 51 and the other guy won? So you do not declare anywhere until you get answers that look like this. If the interval was these numbers, no matter which one of these numbers is, aren't I going to get 50 or more % of the vote? Right? 51 to 50. And so I'm going to win. And if that happened, then you can say Kansas has gone Royalist. Right? Because any one of these numbers is good. Now, there is a caveat to that. My confidence interval is only 95%. Doesn't that mean that 5% of the time I'm going to tell you the wrong thing, right? The interval I came up with isn't right. Which means that, what, 1 in 20, that's what 5% is. Right. So couldn't you end up declaring 2 states the wrong way, right? Your sample said one thing and then later on you find it's the other. And you know, politicians are very touchy about that. Hey, you said I was going to win canvass and then ended up the other guy won. Something bad has happened there, right? Voter fraud, whatever. Doesn't necessarily mean that. Couldn't it just mean that the sample that we got was a little bit more in your favor? The data came out this way, but real life is different. 5% of the time, right? I'm going to be wrong. 5% of the time, you're going to lose, right? When I said you're going to win. And you live with that. So don't listen to politicians who say the prediction was I was going to win and then I didn't. And so that is necessarily a suspicious thing. Now, it could be, right? For instance, I believe in Chicago, you're allowed to vote when you're dead. So there could be some mischief going on, and maybe that's the reason you didn't win. But equally, couldn't there be no suspicion? It's just randomness. So that is us for today. Last name, attendance, and bye-bye. And if I do actually go into politics, will you all vote for me? Because I think having a royalist person in
Maybe.
the Senate would be a good idea. What do you mean, maybe?
That sounds good.
I'd be a really good politician. I wouldn't
Royal
be very,
Robinson?
yeah, I would be very electable because I would tell the truth. And that pretty much guarantees that you'd never get elected.
That's what
So if
every candidate says.
No, every candidate that I know of, virtually, there are always exceptions, tells lies. I mean, that's part of that goes with the job. Yeah, I would be one of those ones that would tell the truth and get into real trouble because of it. So maybe you shouldn't vote for me. That's probably safer. Since I have no intention of ever going into politics, I don't think you need to worry about the choice. Although I think the Royalist Party would be quite good. I mean, think about it. We bring back the Queen, right? We get some of our 11 states back, right? So they can join Britain again. I don't want New York, so you can keep New York. And I don't want California, so you can definitely keep California. But we'll take the good stuff, right? All the other ones. And yeah, you would vote for a candidate that wanted that, wouldn't you? Yeah, okay. Bye-bye for now. I'll hang about for questions.
Okay, so for the next question, it says, suppose 100 such polls are done and each one is used to find a 95% confidence interval, percentage of the population who plan to vote on a certain candidate. And then the question A is, how many of the 100 confidence intervals are expected to cover the true percent? Would it be
95% of them.
Okay, yeah, okay.
And how many are not? 5% of them. They're just phrasing 95% confidence in a sort of a slightly different way, right? If you did 100 times, 95% of the time you would get an interval that was right, and 5% of the time you get an interval that's wrong. That's